This video is about using Autograph and Excel to have a look at the fundamental theorem of calculus. Now, what is the fundamental theorem? Well, I'm illustrating this with a plot of y equals x squared, and from an arbitrary starting point of 1, I've got a point here which is x, and the area from 1 to x is therefore a function of x. Let's just move this around and you can see that it's 0 here and it's 2 1/3 there. So what I've done, I've looked up the values of the area and put them in the spreadsheet. So these are the values of x and these are the values of a. I've obviously extended the number of sig fig to get more accuracy here. So these points here have been put back into Autograph as this set of points down here. It's 0 here and it is 2 1/3 here. Those points there can be fitted by a polynomial function, and the one that fits it perfectly is a cubic function. And of course, if you know your theory of integration, it's going to be one order more than x squared, so that's all fitting quite nicely. Then I thought, well, once you've got this function, let's have a look at the gradient of it. So it's possible to measure the gradient of the integral function. And here the gradient is given by the equation of the tangent, and it's 1. That's very good. And the value of the original function is 1 as well. As we go up here, let's have a look at this one here. Here the gradient is 4, and indeed the function is 4. So putting all these values in a spreadsheet, you can see that what we've got here, these are the values of the area, these are the values of x, these are the values of the gradient of the area function, and they are of course exactly the same as the original function. So we have demonstrated that the integral process is in fact simply an anti-differentiation. So let's just get rid of all this stuff and show you how it was put together. So we'll just do a Control A to select everything, but I'll keep the basic plot of the x-axis, which is y equals 0, and the quadratic y equals x squared. So we'll get rid of the rest, just press delete, and it'll all go. Thank you very much. So what did we do? We put a point at 1, and we put a point at x equals 2. Now if I select that and this, I can ask for the closest point. That'll give me an ordinate down there. So if I select this, and that'll ask for an ordinate closest point. Now I want to put a random point somewhere along the middle, which is my value of x, so that will move up and down. So we want the area from here to here, so now it's a right click, find area. Let's do Simpson's rule, because that'll give you an exact answer for a parabola and for a cubic, of course, and 5 divisions will do fine. So this is where we get our values from, and if I select that and the text box, that'll give me the area. Now what I found when I first did this is that this isn't quite enough accuracy to produce the correct cubic that goes through the points. So I'm just going to go to Page, Edit Settings, and bump this up to 9 sig fig. That'll do. So we get a lot more accuracy. So that's the value that I've 0.581, so that's this one, 1.4. So all we've got to do is just go through these. It starts off with 0 and 1 and just transcribe these numbers. Occasionally it's not a bad idea to actually do some work putting these in by hand rather than expecting a computer to do it for you. I'm all for that, and as you go up here we get the complete set. So this is what we've got here. So if I select these and right click copy, and over here we right click enter an XY data set and right click paste. Here we have the values in here, and if we click OK, it'll produce. I didn't mean to do that because it's rescaled, so I'm just going to undo that and right click enter XY data again, and this time don't perform an auto scale. So here are our new points. So what I'm going to do is, I think we've probably finished with the area function. We don't really need that anymore. Just cluttering up things. Right, so here are the set of points determined by this data down here. So I'm going to select it and I'm going to fit the best fit I can, and after a bit of exploration I found that the cubic fitted absolutely spot on, as indeed it does. Alright, so now I'm going to hide this, and I'm going to put a point at random on here somewhere. It doesn't really matter where it is. I can use the arrow keys to move it around, and I'm going to do a tangent to that. Okay, we've now got slightly too much accuracy, so I'm going to have a look at the page settings and put it back to 4. There we are. And so what we've got now is that the gradient is let's just maybe illustrate this a little better by putting the text box on, and then we've got up here. So clearly the gradient is 1, so I'm just putting 1 here for the gradient. dA by dx. I'm now differentiating the area function, dA by dx. So there it is at point 1, and the answer is 1.21, and so on all the way up to this one, which is 4. So this I think is pretty remarkable, really, that we've got the area function here, and here is the gradient of the area function, and of course it just replicates exactly the original function that we've got. So that is a graphical approach to the fundamental theorem of calculus.